So take a look at this top left corner. What energy do you see and what energy transformations are occurring? There is electrical energy, and it's getting transformed into what two kinds of energy? Light and heat, or light, or you can use the language of radiant and thermal. But you understand light and heat, you bet. The second one, what are the energy transformations? What energy is present? Something is getting transferred into sound energy. Sound is vibration. What is getting transferred into sound energy? What is the air doing? It's moving, so it's kinetic, it's mechanical. Mechanical energy into sound energy. The air's got to move. Am I the bro who needs to slow down? Sure. Are you talking to me? Yes. Okay. Next one. Okay, what's going on here? Top right. Thermal is produced. What else is produced? Heat is thermal. Light energy or radiant energy, same thing. What is being turned into light and thermal energy? What is the energy that's being turned into light and thermal? It's not kinetic. It is chemical potential. Chemical energy into light and heat, or light and thermal energy. Next one. Sorry? It is not electropotential. It is magnetic potential. And magnetic potential is getting turned into? Sorry? I thought someone said it. Kinetic. I wasn't sure if that's what I heard, but I was pretty sure. And this can be really scary. Magnetic into kinetic is pretty intense. Mr. Morrison, for example. In that box right next to Harleen. Yes, thank you for returning the plans. Mr. Morrison has a magnet and iron plate combination that will shatter your hand if you get your hand caught in between. Like actually shatter the bones in your hand. It's such a strong magnet. It's pretty cool. No, we're not testing because it will happen.
What if we get one of those like fake hands?
No. I assure you, it will crush. Yes.
It's like the movie thing that was for Ethan happened.
No, she's describing, so that was what you're describing, Malik, is a Van de Graaff generator. That was electric potential energy into like actual moving electricity. Yours that you're describing is one of those plasma balls. Yeah, it's electric potential energy. But there's something else inside there. Like there's there's a plasma in there that I don't know what it is. There's a gas in there. Different than what Malik was describing. But the effect is the same. Like it's the electric potential energy, the plasma, and the... Oh, Soham is taking over. Okay. So, what's this? It is nuclear potential. Nothing has happened there yet. But not necessarily, but could. This is the fuel, uranium-235. This is used in certain kinds of nuclear reactors and certain kinds of nuclear weapons. It's used in, we'll look at this. We'll look at what kind of nuclear reaction this is in a couple days. I'll tell you right now, though, this is what's used in a fission. Memphis and Imparis, Harbir and Vikram. This is what's used in what's called a fission nuclear device. And a fission, what's special about a fission reaction is that we actually know how to control them. So the working nuclear reactors we have right now are what are called fission nuclear devices. Hey, Bree, put your phone away. And we can control this reaction. When we choose not to control this reaction, that's where you get a nuclear bomb. The other kind of reaction is what's called a fusion reaction. Fusion does not use uranium, it actually uses hydrogen, goes the other way. And fusion is the nuclear reaction that powers our most powerful nuclear bombs, and the sun is what is going on is the kind of nuclear reaction going on in those places. We are working right now to figure out a way to control it, but right now it requires more energy to control the reaction than we're actually getting out of it. So we can't use it as a power source yet. How do you get it, or how do you make it happen?
How do I get it?
Which? The second one or the first one? The first one is hydrogen. It's just you need to go find some hydrogen gas and away you go. The second one, this gets mined out of the ground. It actually gets mined in a different form out of the ground in a few different places. Northern Saskatchewan is one place where you can get this. If you try to purchase it, you get put on an FBI watch list, so don't try and purchase this. But uranium is an interesting one because uranium actually glows when you put a black light on it. And so people, before they realized how nasty this stuff was, they actually used it in dishes. You can find, if you take a black light or a UV light, like a UV flashlight, and go to like MCC in Value Village and shine the lights on the glass that's there. If any of that glass starts to glow, it's actually uranium glass. Buy that. It's really cool. You cannot use it to make a bomb, but it is radioactive. If you decide to do this and you find this stuff, by all means, bring it to class. I will happily reimburse you for it. I've been looking for uranium glass for a long time and haven't been able to find any. But it's out there. People with glassware from the 60s and 70s have this stuff. And you can actually buy necklaces that have uranium glass built into it. It is slightly radioactive, not radioactive enough to kill you, but slightly radioactive, and it glows really cool under black light and UV light. So we'll talk about that one in a week or so. What is this? It is gravitational potential into what? Gravitational to what? Kinetic. Because the water's moving. What's the next one? Elastic. That is what you were supposed to see there. No one in the other class saw it. They're like, no way. Yep, that's an elastic band. Wrapped around these letters, that's what you were supposed to see. What's the next one? What is represented by a burger and fries? What kind of energy is food? No. Sorry? It is chemical and potential. And as it sits right there, it is only chemical energy. You eat it, and then your body turns the chemical potential energy into useful energy. Your body turns it into heat. Your body turns it into elastic, which turns it into kinetic. You do all sorts of stuff with the energy in the burger you ate. And if you don't do anything with the energy you get from the burger, that's how you get fat. Because constantly consuming more energy than your body needs is how you put on a ton of weight. Yep. If you consume exactly the amount of calories your body needs, you maintain weight. And if you consume less calories than your body needs, you lose weight. Because your body will take from what is part of it already to make up the loss. Okay, what's the last one? It's something turned into mechanical. It is magnetic. That is a magnetic levitation train. You bet. They're very cool. Does anyone want to explain what's going on there? Okay, Malik wants to try and explain. Okay, so there's two opposite magnets. So the track looks like this. There's a bunch of magnets on the track. And then there's a bunch of magnets on the train. So Malik, what you're suggesting is we need opposite magnets. So if this is a north pole, and that's a south pole, and that's a north pole, that's a south pole, that's a north, actually that needs to be a south. That needs to be a north. That needs to be a south, south, north, north, south. Okay, so let's zoom in on this and I'll show you what's happening here. What do opposite poled magnets do to each other? They attract. What do the same pole of magnets do to each other? They repel. So what happens is you get a setup where on the track it looks like this, on the train it is the opposite. So this magnet on the track pulls this magnet forward, and this magnet pushes this one forward. So you get two effects on this magnet, a pull from here and a push from here. This magnet gets attracted to this one and pushed from this one. This one gets attracted to this one, pushed from this one. This one gets attracted to this, pushed from this. And same thing with this one gets attracted to this. These two objects do not touch each other. There's no sliding. They hover above each other because this one's repelled up by this one, this one's repelled up by this one, this one's repelled up by this one, this one's repelled up by this one. So that's how it levitates up off the track and it gets pushed forward. Yes? How would it get pushed back? This one pushes here, this one pushes here, this one pushes here, this one pushes here. Because these are opposite, so this one pulls this way, pulls, 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 pulls. These two and these two. Because opposite magnetic poles. Oh, why doesn't this one slam down into here? Is that what you're asking? You can make that happen as long as if this one is stronger than this one, the push up from here will be stronger than the pull down from here. That's the beauty of this. The train cannot crash. Because if you look at it from the side, the track is in the middle in the shape of a T, and the train itself is in the form of a C. So this is the track, this is the train. The magnets are all along the outside here and all along the inside here. So this train is not going to derail. What's the worst thing that could happen? The train, no, you can't go up. You can't go up because it's hooked on the bottom. You can't go up. And that's the beauty of this. You cannot go up. All these magnets are what are called electromagnets, which means you need electricity to make them work, which means, so if the electricity is going one way, this is the pattern that's produced. If you flip the current, the opposite will be produced. It'll go south, north, south, north, south. So it'll push the train back, slowing it down. If the power gets cut to these magnets, what's the train going to do? It's just going to slam onto the track and slide to a stop. These trains are very, very safe. They're very easy to move. There's no friction here because the train is floating. If you got behind this thing and pushed, you could slide the train. There's no way you're doing that to the SkyTrain. But if you managed to survive getting onto the track and didn't get electrocuted, you could push the train forward as it floats there because there's no friction. It's really, really quite a cool system. It's expensive because you need a constant source of large amounts of energy to make these magnets happen. And it's expensive to produce, but once you've made the thing, you have a very safe, very reliable, very fast form of transportation. It's really quite a cool system. It's not practical here, which is why we haven't done it. But in a densely populated area, or in like where you have life all along the track, Japan, for example, China, a very densely populated country, you have, it becomes financially worth having trains like this, where it's not worth it in Canada. The amount of money it would cost to connect Vancouver and Calgary, never mind the mountains that we have in the way, but even Calgary to Winnipeg with tracks like this would be astronomically expensive. And the number of people who would do that train ride, they may as well fly. But in Japan, China, Korea, you have massive need for transportation systems like this. It's really quite cool. Okay. Sorry? No, SkyTrain is not a magnetic levitation train. There's actually wheels on the track there. Yes, Malik.
So like the ground, like the tracks that have shoes, like a train wheel.
Yes.
That's like hover above the ground.
Yes, until you hit the next magnet and you slam to the track.
And then you get electrocuted.
You need the length because it's the length that gives you the alternating magnets. If it was you with shoes, you'd need really tiny, strong magnets. It is technically possible.
So when the
It would be technically difficult, but it is practically possible.
train needs to stop, how does it stop?
It switches the magnets on the bottom.
And it slams into the ground.
No, it doesn't cut the magnets at the bottom, then it would slam to the ground. If you make, so this is the pattern you have here. The north, if this one pushes forward, attracts to, actually that's not the picture I gave you. This is the picture I gave you. The way this is right now is this magnet is getting pulled to here and pushed from here. If this was a south, all of a sudden this changed to a south, it would push backwards against this one. And if this was a north, it would pull back. So to slow one of these trains down, you just change the direction of the electricity and it changes these magnets. From this would become a south, that would become a north, and it would drag the train back.
So the electricity next.
It just goes in reverse, yeah. It's constant, and so this gets expensive. You need a large power source to do this. Does anyone know Japan's primary electric generating system? It's nuclear. Many nuclear power plants. Japan's a really cool country. Get on a bullet train. It's gonna be awesome. In 49 days or for 49 days? I would love to go to Japan. Japan would be so cool. Okay, so let's do a couple of these. The picture is not necessary. There's just the descriptions at the bottom. What are the energy transfers or transformations in these scenarios? So, a ball is thrown. The result is mechanical because you have a moving ball. But what are the energy transformations required to make this happen?
Kinetic.
No, kinetic is the end. Gravitational is not a part of it. Chemical is where all of this starts. But your body turns chemical into what? Your body turns the chemical energy it eats into what kind of energy that allows you to throw the ball? No, because that is what happens at the end. There's an in-between one. How does your body throw a ball? How did you just do that, Lexi? How did you pick up your arm? No. What part of your body allowed you to pick up your arm? Your brain told what to do, pick up. The nerves controlled what? The muscles is what we're looking for. Your muscles demonstrate what form of energy? Does anybody know? Elastic. I didn't hear it. You ought to be more assertive. Your body, your muscles are a form of elastic potential energy. If you tear them off of the muscle, they will roll up inside your body. Mr. McWhinney did this to himself a couple years ago. No, doing a pull-up in the gym for some students. He tore his bicep off the muscle doing a pull-up in gym class. It rolled up inside his arm. I can't remember if it tore from the top or the bottom. I think it tore from the bottom and slid up. He had to go have it surgically reattached. It was awful.
So like if I work out, play sports, there's no chance that my muscles tear off.
If you don't prepare properly, like what that's, so guys, okay, there's too much conversation happening over there, gentlemen. Josiah asked a good question. So if I go and do sports and train really hard, there is a potential this could happen. Yes, there is a potential this could happen. But what do we do in an effort to prevent this? Stretch and warm-ups. That is the purpose behind stretching and warming up. You're giving your body a little bit of light repetition so that your body becomes prepared to work. If you do any of those high-intensity exercises, you go play a sport and you're cold, that's where you have the potential to injure yourself. It's less common that your bicep tears. It's more common that you actually tear tendons down in your ankles and knees. But that's all that is. If any of you have ever seen an Achilles tendon injury, it rolls up. It's a little floppy. Rolls up inside your. Oh, it's gross. It's disgusting. Not a chance. No. I don't want to watch that. You can go look that up later. It's gross. But you can hurt yourself because it's all elastic potential. Okay, let's do another one. Let's do the children playing. The children playing. Yes, that's exactly my point. Yes, Josiah. The children playing are exactly the same as this one. Chemical, elastic, mechanical. The result is different. The energy transformations are the same. Love it. How about hot food sitting on a table? It's thermal to what? Chemical potential. You betcha. You cook the food, now it is consumable. You have a particular kind of chemical energy waiting there for you. Love it. Let's do one more. Ice cubes melting. What is that a demonstration of? It is not chemical. It is thermal into what? Not chemical. What happens when ice melts? You get water. How is water different than ice? Because chemically it's the same. H2O is H2O is H2O. Thermal does what? Oh, say it again, Josiah. It's kinetic. What thermal does is thermal allows the solid water molecules to start to move, turning them into a liquid. Melting ice is thermal to kinetic. If you add more thermal, you'll get more kinetic until eventually the water turns into what? If you add more thermal, you'll eventually get more kinetic. And if you get more kinetic, the water will turn from a liquid into a gas, and we call it steam. That's all it is it's allowing thermal energy to turn into kinetic energy. If you take thermal out, you can decrease the kinetic and it'll get solid again. That's steam. Yes, kinetic again. Okay, flip the page. Here we go. This is the new stuff for today. Okay, so you stay on this page. I'm going to flip back. We're going to start doing some of the math to figure out just how much energy do these objects have. So you stay on that page. I want all your attention up here on the screen. Malik, put your phone away. Malik, put your phone away. So when we were discussing last week, we discussed kind of anecdotally spring potential, gravitational potential, and mechanical. I demonstrated a few things for you, and I said a way for you to think about how much energy these things have, or different objects have, is if this thing hit me, how much would it hurt? The more it would suck, the more energy these things have. And when we were looking at mechanical specifically, the example I gave was me and my son. If my son and I are moving towards you, and you're thinking about which one of us would damage you more, I have more mass than my son, it's probably going to be me. If you talk about impulse control, it's probably going to be my son because he doesn't have impulse, he's 2. He will hit you before I will. But if both of us decided to hit you, I would hurt more because I'm bigger. But if I took my son and he was walking at you versus my son was running at you, now you have to be a little bit more cautious. Because my son, if he's walking at you, you could stop him easy. If my son is running, so like what my son and I will do when we're at home, when I get home today, in about an hour, hour and a half, in the hallway, my son will see me from a distance. My son goes, "Daddy!" and he runs full speed, and his head is right around stomach level. So if I don't prepare myself to catch him, it is a very uncomfortable experience. Because his head is like here, his shoulder is slightly lower. If I'm not prepared to stop him, I'm taking the full force of him. Keep your hands to yourself, Barbier. I take the full force of him to my lower torso. Uncomfortable experience, to say the least. Getting punched in the stomach with a little 35-pound bowling ball of a dude, okay? So, anecdotally, just conversationally, we said that when you're talking about mechanical kinetic energy, Malik and Soham, the mass of the object and the speed at which it's moving are the important things to consider. Now, today I'm going to give you the equation that relates all of these things together. Where this thing comes from, Josiah, Soham, and Malik, where this thing comes from, I am not going to get into, because where it comes from is actually kind of a complicated mathematical discussion. I didn't even really tell my physics students. I just showed them this, and they're like, yes, the equation for kinetic energy is 1/2 mv squared. Because my physics 11 students don't have calculus, and you need the calculus to see where this comes from. So let's just say for the time being, trust me, the equation that governs how much kinetic energy an object has is this equation right here, 1/2 Himparis and Vikram, pay attention please. 1/2 times the mass times the velocity squared. The mass is given to you, it will be given to you as kilograms, it must be in kilograms. The speed of the object will be given to you in meters per second. Now, meters per second is not a unit you guys are probably familiar with. So let's just do a quick, the one that you are familiar with for speed is what? Kilometers per hour. That is usually what people are familiar with when we're talking about velocity. Say, oh yes, kilometers per hour. So just to give you perspective, the relationship for kilometers per hour and meters per second looks like this. Again, if you want to know where this comes from, this I will show you next year if you take my physics class. But for now, just take my word for it. If you want to go from kilometers per hour down into meters per second, you have to divide by this number 3.6. And if you want to go the other way, from meters per second into kilometers per hour, you have to multiply by 3.6. So just to give you a rough idea of what this looks like, you guys should be familiar with this number, 100 kilometers per hour. 100 kilometers per hour is the speed at which a car will travel on the highway, assuming the driver is obeying all posted speed signs. Good thing Josiah's not behind the wheel yet. You don't have your N, you're not allowed to drive alone. Actually, he's not. Nowhere are you allowed to drive on your own with an L. Parking lots are private property. A cop will absolutely give him a ticket on a parking lot. Not even there. No, not even there. It's against the law. So, to give you guys perspective, okay, stop talking. 100 kilometers per hour, Lucas, stop talking, Josiah, stop talking, is roughly 27 meters per second. So, when we look at this, the equation for kinetic energy is 1/2 times the mass times the velocity squared. Mass is measured in kilograms, velocity is measured in meters per second, and we're squaring it. So if I look at the units for kinetic energy, you'll see that the units here are actually kilogram meters squared per second squared. That is a ridiculous set of units. That is a set of units you guys are not familiar with, because we don't use that energy use that unit for energy. When we're talking about energy, does anyone know the units we use? And it's actually written on the page. Units for energy are joules. Because that is a ridiculous expression of units, we simplify it, we condense it, and we name it after a dead guy who did a lot of work in this field. The dead guy's name is Joule, last name was Joule, and he was a British physicist. So we do this with all sorts of units. We do this with forces. When you guys are going to talk about forces now, but in Physics 11, when we talk about forces, a force is given as a kilogram meter per second squared. That's a ridiculous unit. So we name it Dennis after the guy responsible for doing a bunch of work with forces. When we think about forces, the name that should come to all of your minds, even if it doesn't yet, is Sir Isaac Newton. Isaac Newton is the dude who did forces, and so we give the units of force as newtons. I'm right there with you, man. That's not where I'm at. I thought you were vibrating with frustration. Yes, if you invented something cool that no one else had invented and the units were stupid, we could call it we could simplify it to the, what's your last name, Luca? It's something awesome. Arakovich?
Oh, that's beautiful. Oh,
Yes, the Arakovich. Let's call that the unit of Dawidoff's current frustration. No, you just won't stop talking and so are frustrating me. Imparis is increasing the Arakoviches in the classroom, the units of my frustration, because Imparis won't stop talking either. Okay, let me get through this. I am almost done. So, kinetic energy, the energy of motion, can be found by taking the mass of the object, its speed squared, and multiplying it by a half. So which of these is the most important portion of the movement? Which one's going to jack up the energy the most? Is it the M? Which one has the largest effect on the math? Because what are you doing to the velocity, Dennis? No, but mathematically, what are you doing to the velocity? You're squaring it. Squaring it means multiplying it by itself. So you're going to take the velocity, you're going to multiply it by the velocity, and then you're going to multiply it by the mass once. So the speed at which you're moving is the largest contributor to how much kinetic energy you have. So let's do 3 examples, and then you're on your own to play. First example. You have a 20-kilogram koala. That is a large koala. Koalas do not get this big. Koalas are small. Koalas are slow. Koalas are stupid creatures. Just they are. They're small, they're slow, they're stupid. They pee on themselves, so they constantly smell like urine, and they all have the sexually transmitted disease chlamydia. No, I do know. I have interacted with koalas on a meaningful level before. They're adorable, but they reek and they're stupid and slow. How they have not gone extinct, I do not know. So you have a 20-kilogram koala crawling, crawling at 5 meters per second. Okay, crawling is generally when we think of crawling, we think of an object moving slowly. Just so we're really clear on what 5 meters per second is, let me demonstrate. I have 5 meter sticks here. That's 1 meter, 2 meters, 3 meters. This is exactly my point, Malik. 4 meters, 5 meters. So you have a koala, allegedly, moving this distance every... That's the beat. Okay? You can do that? You want to run it? It is exactly 18 kilometers per hour. So that's 2/3 of the speed limit in a school zone. That is almost the world record for human sprinting. No. You do 35 miles an hour? Pretty sure slower than that. 25? I'm pretty sure slower than that. I'm pretty sure Usain Bolt is slower than that. We'll look it up. I'll look it up. I could be wrong. I'll look it up. I'll look it up. Let's look it up. Usain Bolt top speed in kilometers per hour. Okay, 45, you were right. You were right. So it's half. It's just under half of the fastest human alive. Okay, so let's say a koala could actually do that. It's not likely. Do what you got to do, but we're going to go for it. So here is how I want you to set up this work every time you do it. I want to see everything I'm about to demonstrate. Okay, so we see here, we want to find the kinetic energy. The first, as soon as you have identified what you want to find, you're going to go and you're going to grab the formula for it. I'm going to give you 3 different formulas: kinetic energy, gravitational potential, and spring potential. And once you know which one to use, the first thing you do is write it down. Kinetic energy is 1/2 mv squared. And then I want you to go ahead and write down what you know. We know that the mass is 20 kilograms. We know that the velocity is 5 meters per second. And now we're going to go ahead and substitute it. If you don't do this the way I'm demonstrating it, I will not, I know all you care about is how you're going to do on a test or a quiz. You will not get full marks unless I see all of the work that I'm demonstrating right here. I don't care if the answer is correct or not. I want to see the method. So we're going to have, yes, 1/2. Every time you replace a variable with a number, you have to put brackets where that letter was. So we're going to put brackets where the m was. We're going to throw a 20 in there. We're going to throw brackets and a squared, and we're going to throw a 5 in there. And now we're going to go ahead and calculate this thing. You don't need a calculator for this, because 1/2 of 20 is 10, and 5 squared is? Nope. 25. 10 times 25 is what, Angel? 250 joules. I want to see all of these pieces. At this stage, you may get a calculator. But I want to see all this work. Okay, next example. Number 2. Yes.
As long as we like have those steps, but we don't have to multiply and addition.
Okay. It's unlikely. I mean, unless Usain Bolt played rugby, he could do it.
Yeah, right now.
Because this is 36 kilometers per hour. You're right. Your average rugby player is not going to be doing this. Okay, so, but let's say they were able to. Hands up if you're a rugby player here in the class. Okay, let's see if we can find a 75 kilogram rugby player. Just so we've got perspective.
How much is that in pounds?
Wait, around how many?
Okay, if you're a rugby player and you think you might be around 75 kilos, step up. Malik, get on the scale. Okay. Malik is
I'm the closest.
57. I had a female rugby player who was more than that.
I'm the last person. I weigh 1.
Okay. 62. Do I have anyone bigger than rugby players bigger than Luca?
I'm not rugby, but come on, Memphis.
Oh, here we go. Luca's 70. We're almost there. Harvey, play rugby?
Memphis is the
Sure, let's hop you on here. Let's say Harvey plays rugby.
Come on, Memphis.
We're getting slightly bigger.
Yeah, let me go right across.
Okay. Can I announce the class? 90.
Yo,
90
you almost have
kgs.
my CFP.
Okay, so we're a little bigger. So here's what we're gonna do. Luca, hop back on here. Luca was our rugby player.
That's Memphis.
So it's Luca plus, hop on there. Hold on. 1, 2, 3, 4, 5. It's Luca plus this. There we go. Oh. There we go. This is the person who's doing this run. Just I think, I don't know if it does helps you or not, but I like to visualize these things. And Luca, carrying that blue tin, is running 2 of these distances every second.
Yeah, not happening.
Not happening. I mean, I would be very impressed. Luca should actually go, he would win BC track provincials if we were doing this. So let's say if Luca was able to do that, how much energy would Luca have? Okay, write it out. EK equals 1/2 mv squared. The mass is 75. The velocity is 10. We're just going to plug it in. 1/2 times 75. I'm going to need that number in a second again. squared equals what? 375 joules of energy. Sorry? I think there might be an extra zero here. Because half of 75 is, oh no, it's not.
37.5 times 100.
Yes, 37.5 times 100. Yes, there needs to be an extra zero there. Boom. 3,750, that makes more sense. Okay. Last one. This question says, which of the following has more kinetic energy? Do not go ahead and do this question. Stop. Pause what you're doing. Because I'm going to change the question. To put things in perspective, a golf ball moving at 900 meters per second is a golf ball moving at 3,240 kilometers per hour.
Yeah, no.
Which is, no, because that is 2.6 Mach. 2.5 times the speed of sound. It is not it's not physically possible. The world record for golf shots is, Ryan Winther, 349.38 kilometers per hour. So what we're going to do is we're going to knock a zero off that. 90 meters per second is 320 kilometers per hour. We're changing 900 to 90. That is a totally reasonable golf shot. The average professional hits just under 300. The world record is 350. So this is like a very intense professional. Tiger Woods could do this. So, which of these has more energy? A golf ball moving this fast, 90 meters per second, or a 1 kilogram ball moving at 10 meters per second? 1 kilogram is 2.5 pounds. That might be like a 5-pin bowling ball, maybe. Sorry? Just to give you perspective, to help you understand what this means. I'm showing you what 90 meters per second is. It's 320 kilometers per hour. That's like an F1 car. Very fast. So, let's figure this out. EK is 1/2 mv squared equals 1/2. The mass is 0.01 kgs. The velocity is 90 meters per second. So we're going to have 0.01 times 90 squared. What's that number? I feel like I need a calculator. 90 squared is 8,100 times 0.01 divided by 2 is 40.5. 40.5 joules. So not a lot. Let's say you took a 1 kilogram object, 1,000 grams, and you launched it at 10 meters per second. 10 meters per second is 36 kilometers per hour. How much kinetic energy would it have? Well, EK equals 1/2 mv squared. M is 1, V is 10. So it's going to be 1/2 times 1 times 10 squared. That's easy math. 10 squared is 100, times 1 is 100, and then half of 100 is 50. So the 1 kilogram object moving at 36 kilometers per hour or 10 meters per second has slightly more kinetic energy than the golf ball going at 90 meters per second. Which means it would suck more if that 1 kilogram mass hits you than that golf ball. Golf ball would hurt. Don't get me wrong. Like that would be exceedingly painful. Flip the page. Yeah, 4. I love it. Okay, here's your homework. These 6 questions. On your market set giver, you have like 12 minutes. You can easily get this done. May the force be with you. Yeah, go ahead.